Based on what you were describing, this could soon be the biggest story in the world. Literally the biggest story in the universe.
Right now, amateur astronomers around the world are capturing something that's making professional scientists question everything they thought they understood about interstellar objects. A Hawaiian observer known as KalopaStars has just released what experts are calling the most structurally revealing image of 3I Atlas ever captured, and what it shows is stopping researchers dead in their tracks. We're not talking about fuzzy blobs or distant smudges anymore. This new image reveals geometric structure, sharp edges, and features that don't match any natural comet we've ever observed. Multiple independent astronomers from Japan to Spain to Chile are all photographing the same impossible details, meaning this isn't equipment error or wishful thinking. This is real data showing real structure on an object that formed around another star billions of years ago. What makes this absolutely extraordinary is that these amateur observers, using telescopes you can buy online right now, are documenting anomalies that billion-dollar space telescopes somehow missed or haven't publicly discussed. By the end of this video, you'll understand why these backyard discoveries are forcing the scientific community to confront uncomfortable questions about what 3I Atlas actually is. But before we dive into these shocking images, make sure you hit that subscribe button and turn on notifications, because 3I Atlas reaches its closest approach to Earth in just 18 days on December 19th, and what happens between now and then could fundamentally change our understanding of what's possible in the universe. And if you're as blown away by this as I am, smash that like button, because this story needs to reach everyone who cares about cosmic mysteries. Let me set the stage with why these amateur observations matter so much. When 3I Atlas was first discovered on July 1, 2025, by the Professional Atlas Survey Telescope in Chile, it immediately became the target of virtually every major observatory on the planet. NASA's Mars spacecraft captured close-up views in October. The Hubble Space Telescope imaged it in July and again in November. The James Webb Space Telescope conducted detailed spectroscopic analysis in August. The European Space Agency's spacecraft at Mars tracked it continuously. We're talking about billions of dollars of equipment, the finest scientific instruments humanity has ever built, all pointed at this one object. Professional astronomers have been studying it for 5 months with every tool at their disposal. And yet, some of the most revealing and structurally detailed images didn't come from any of those professional instruments. They came from amateur astronomers operating backyard telescopes from their homes in Hawaii, Japan, Spain, and Chile. KalopaStars in Hawaii captured an image that shows what appears to be geometric structure with defined edges. Mitsunori Tsumura in Japan photographed tightly collimated jets extending millions of kilometers with laser-like precision. Paul Craggs captured what some observers describe as an elongated, almost ship-like morphology. These aren't professional astrophysicists with institutional backing. These are dedicated hobbyists who love astronomy enough to stay up all night capturing data on an object that mainstream science keeps insisting is just a normal comet. But here's where things get really interesting, and this is where the amateur community is making discoveries that challenge official narratives. The Hawaiian images from KalopaStars show structure that appears far more defined than what you'd expect from a natural, irregularly shaped comet nucleus surrounded by a fuzzy coma of gas and dust. Natural comets are messy. They're chunks of rock and ice that have been tumbling through space for billions of years, accumulating craters and fractures, with surfaces that sublimate unevenly, creating chaotic outgassing patterns. When you photograph a natural comet, you typically see a bright central region that's the nucleus, surrounded by a diffuse coma that fades gradually into the background. The edges are soft, irregular, fuzzy. What KalopaStars captured appears different. Multiple observers have noted what they describe as sharp boundaries, geometric features, and structure that maintains definition across the breadth of the object. Now, could this be an optical effect? Could specific lighting angles or dust distributions create the appearance of sharp edges on what's actually a natural irregular nucleus? Possibly. That's what skeptics argue. But when multiple independent observers using different equipment in different locations all capture images showing similar structural characteristics, that consistency demands explanation. It's not just one person seeing what they want to see. It's a pattern across multiple independent data sources. And the mystery deepens when we look at what these amateur images reveal about the jets. On November 22nd, Mitsunori Tsumura in Japan captured an extraordinary image using a half-meter telescope that shows both an antitail pointing toward the sun and a much longer tail pointing away. What's remarkable isn't just that both tails exist, but how they're structured. The antitail extends approximately 1 million kilometers toward the sun, pushing through the solar wind, which flows at about 400 kilometers per second in that region. For that antitail to maintain coherent structure while penetrating the solar wind requires enormous momentum flux. Harvard astrophysicist Avi Loeb calculated that the mass loss rate required to produce what's visible in these amateur images amounts to roughly 10% of the comet's estimated minimum mass over just 2 months. That's a staggering amount of material to lose without the nucleus fragmenting or disintegrating, which is what normally happens when comets shed that much mass that quickly. The Japanese image also shows the tail, extending about 5 million kilometers in the opposite direction, also tightly collimated, also maintaining structure across vast distances. Natural comet tails tend to spread out and become more diffuse with distance because the dust and gas particles have slightly different velocities and the solar wind disperses them. These tails look almost laser-focused, maintaining narrow profiles across millions of kilometers. That's unusual. That's worth investigating seriously. Wait, there's more to this story that connects the amateur observations to something even more extraordinary. On November 17th, French astrophotographer François Kugel captured images showing multiple distinct jets emanating from the nucleus, each pointing in different directions. Some point toward the sun, some away, others appear oriented at various angles. This isn't the pattern you'd expect from a randomly shaped nucleus with ice deposits that sublimate when heated by sunlight. Natural cometary jets typically correlate with the sun-facing side being the hottest and most active. You get asymmetric jets if the nucleus has an irregular shape or varying ice composition across its surface, but they generally point outward from active regions that are being heated. The multi-directional jet pattern visible in the French images, combined with observations from Satoru Murata in New Mexico on November 16th showing similar morphology, suggests something more complex is happening. Each jet maintains collimation, each points in a specific direction, and crucially, they don't appear to sweep around as the nucleus rotates. 3I Atlas has a confirmed rotational period of 16.16 hours. If these jets were caused by stationary active regions on a rotating nucleus, we should see them sweep across the sky like lighthouse beams as the comet spins. Multiple observations over multiple nights should show different jet orientations as we catch the nucleus at different rotation phases. That's not what observers are consistently reporting. The jets appear to maintain fixed orientations relative to the sun and the comet's direction of motion, despite the rotation. That's one of the documented anomalies that makes this object so puzzling. Now here's where the story takes a dramatic turn into territory that makes mainstream astronomers deeply uncomfortable, but which the amateur astronomy community is documenting with increasing clarity. The structural details visible in these backyard images are raising questions about whether what we're seeing is entirely natural. Paul Craggs in the UK captured an image on November 22nd that shows what he describes as an unusually elongated appearance. Now, Avi Loeb has suggested this might result from motion smearing during the exposure, where the comet's movement against the background stars causes the image to blur slightly in the direction of motion. That's a reasonable technical explanation, but other observers have noted similar elongation in their images, and some have pointed out that the morphology appears consistent with an object that has structural rigidity rather than the loose agglomeration of rock and ice we expect from comets. Natural comets are often described as dirty snowballs, loosely bound collections of ice and rock held together by weak gravity and ice acting as cement. When they approach the sun and heat up, they often fragment because there's not much structural strength holding them together. 3I Atlas has passed through perihelion, its closest approach to the sun on October 29th, where it was heated intensely, and according to all available observations, it maintained structural integrity. It didn't fragment, it didn't break apart. Despite allegedly losing billions of tons of material based on the jet activity visible in these amateur images, the nucleus appears intact. If you're still watching, remember to hit that like button, because what I'm about to tell you next connects these structural observations to an extraordinary precision that seems almost impossible to explain naturally. The non-gravitational acceleration visible in these jets has been precisely measured by NASA's JPL Horizon system, using data from 230 observatories worldwide. The detection is statistically significant at 10 standard deviations, meaning it's absolutely real. The acceleration value is 5 times 10 to the negative 7th astronomical units per day squared. That specific magnitude produced a trajectory correction during the comet's perihelion passage in late October that altered its future path by exactly the right amount to bring it to Jupiter's Hill radius on March 16, 2026. The closest approach distance to Jupiter will be 53.445 million kilometers, identical within measurement uncertainty to Jupiter's Hill radius of 53.502 million kilometers. The Hill radius is the boundary of Jupiter's gravitational sphere of influence, the ideal location for deploying satellites that can maintain stable orbits with minimal fuel expenditure, because they're at the equilibrium point between Jupiter's gravity and the Sun's gravity. The probability of this being a random coincidence is approximately 1 in 26,000. The amateur images are showing us the mechanism by which this precision trajectory adjustment is being achieved. The collimated jets visible in photographs from Hawaii, Japan, Spain, Chile, France, and New Mexico are oriented in directions that would produce the thrust vectoring needed to fine-tune a trajectory to this level of precision. Make sure you're subscribed with notifications turned on, because what happens over the next 18 days as 3I Atlas approaches Earth will be absolutely critical. On December 19th, the comet reaches its closest approach at 269 million kilometers, about 1.8 astronomical units from Earth. That's still very far, almost twice the Earth-Sun distance, so there's absolutely no danger. But that geometry means observing conditions become optimal. Amateur astronomers around the world are organizing coordinated imaging campaigns to capture as much data as possible during this close approach window. The Virtual Telescope project in Italy is hosting live observation sessions. Amateur networks in the United States, Europe, Australia, and Asia are all planning simultaneous observations to provide different viewing angles and continuous monitoring. This is citizen science at its finest. Dozens or hundreds of individuals contributing observations that collectively provide coverage no single professional observatory could match, and they're capturing details that matter. The structural features visible in the Hawaiian images, the jet morphology documented by Japanese and European observers, the temporal evolution of the coma photographed by amateur networks, all of this constrains theoretical models and helps us understand what this object actually is. The professional astronomy community's response to these amateur observations has been fascinating to watch and honestly somewhat troubling. Some researchers are embracing the contributions, acknowledging that amateur astronomers provide valuable continuous monitoring and often catch transient phenomena that scheduled professional observations miss. Other scientists have been dismissive, suggesting that amateur equipment isn't properly calibrated, that image processing by non-experts introduces artifacts, or that observers are seeing patterns that aren't really there. But here's the problem with that dismissive attitude. When dozens of independent observers using different equipment in different locations all document the same features, the same jet patterns, the same structural characteristics, you can't simply wave that away as amateur error. The consistency across independent observations is powerful evidence that what they're capturing is real. Peter Carson Lee in Spain sees it. Elena Walter in Chile sees it. Francois Kugel in France sees it. Satoru Murata in New Mexico sees it. Mitsunori Tsumura in Japan sees it. KalopaStars in Hawaii sees it. Stuart Atkinson in England, using a $500 smart telescope that professionals mock as a toy, sees it. At what point does the professional community acknowledge that maybe, just maybe, these citizen scientists are documenting something genuinely anomalous that deserves serious investigation rather than reflexive dismissal? The honest answer is that we're witnessing a paradigm shift in how astronomical discovery works. Throughout most of human history, major discoveries required access to rare, expensive instruments controlled by institutions. The discovery of Neptune, the detection of quasars, the mapping of the cosmic microwave background, all required professional equipment and teams. But we're living in an era where technology has democratized observation. A dedicated amateur with a few $1,000s of equipment and the knowledge to use it effectively can now capture scientifically valuable data on interstellar objects. The clearest structural images of 3I Atlas, the most detailed jet morphology, the continuous temporal monitoring that reveals how the object's activity evolves night by night, much of this is coming from backyard observers. That's historically unprecedented. That's a fundamental change in how we explore the cosmos. And it means that the next major discovery, the observation that finally answers whether 3I Atlas is a natural, if exotic comet or something that challenges our assumptions, might not come from Hubble or Webb or the Very Large Telescope. It might come from someone's backyard in Hawaii or Japan or Spain, from an amateur astronomer who loves the stars enough to stay up all night pointing their telescope at something nobody fully understands yet. Drop a comment below with your thoughts. Do you think these structural features visible in the amateur images represent natural, if unusual comet morphology, or are we looking at something that demands a more extraordinary explanation? Have you tried imaging 3I Atlas yourself? If you have a telescope, even a small one, the next 18 days are your window to contribute to this historic observation campaign. Share this video with anyone who loves astronomy and citizen science, because what we're witnessing is the democratization of cosmic exploration. The barriers between professional and amateur astronomy are dissolving. The next crucial observation might come from anyone with clear skies and determination. Whatever 3i Atlas turns out to be, whether it's an extraordinarily unusual natural comet that teaches us about exotic stellar environments and planetary formation, or whether it represents something that fundamentally challenges our understanding of what's possible, the amateur astronomy community will have played a defining role in documenting its behavior and pushing the scientific community to take these anomalies seriously. The next 18 days, as amateur observers around the world capture the most detailed images, yet during close approach, will provide data that astronomers will analyze for years, possibly decades. Until next time, keep looking up, keep capturing data, and remember that you don't need a billion-dollar telescope to contribute to humanity's understanding of the universe. Sometimes all you need is curiosity, determination, and the willingness to point your camera at something that makes you wonder.